So our first task for understanding vector fields is to come up with a way of visualizing, sort of how can I understand vector fields from a, first of all, a numerical sort of data-driven point of view, and then also from a graphical. How can I draw a picture that sort of shows me what a vector field is all about? And so the example that we worked through in this preview activity asks us to kind of think about a vector field as being kind of like a wind speed or a wind velocity field. This would be a great meteorology example, right? It sort of shows us which direction the wind is blowing at each point in the xy plane and how strongly the wind is blowing at each point in the xy plane. And so what we're going to do in part A here is think about a vector field that has the formula f of xy equals y comma x. Real quickly, before we go forward, I want to point out a very careful use of notation that our authors are using here. Again, we're thinking of our vector field as a function, which you're going to denote by a boldface f, so that means it's a vector-valued function, right? Because we use boldfaces for vector quantities. And the input to that function is a point xy. So because a point xy describes a location in the xy plane, they're using parentheses around that x and y. But then the output from this function is a vector that we're using angle brackets to denote. And what the angle brackets tell us is that that's a direction vector. So what it means, what typically we're going to do with these vectors when we visualize them later on in this activity, is we're going to compute the direction vector using the formula for the function, and then we're going to place the initial point of that vector at the location which is specified by the input to the function, x comma y. So for example, if f of the location 2, 1 gives us the vector 1, 2, then we're going to draw the vector 1, 2 with its initial point, its tail, at the point 2, 1. Right? So that's how we keep the location and direction information simultaneous in the diagrams that we make that visualize vector fields. So in parts A and B, they're just kind of asking you to fill out a table of values for what are the values of these vector fields at each of the different points that are given to us here. Then in part C, we'll go from the numerical data-driven point of view to a graphical point of view to visualize the vector fields that are there. And that's where this preview activity is going to wrap up. All right, so far so good. So to study vector fields from a sort of data table perspective, all that we really needed to do was plug in these xy locations into the formula for our vector field, and then it spits out these direction vectors. So for the vector field, f of x and y is y comma x. As you said in your groups, all we're doing is we're reversing the x and the y coordinate or whatever location that we're given, and we're making that the components of the direction vector. So f of 2 comma 1 gives us the direction 1 comma 2. And the vector field g of x and y equals minus xj. Another way to write that would be as the direction vector with components 0 comma minus x, right? Because it has no I component, as you say. The I component, the x component of the vector is going to be 0. And so when we feed the location negative 2, 0 into this vector field, we end up getting 0 comma the opposite of negative 2, which is positive 2. So there's the data table perspective. Where we want to go next with this, we don't spend long on the data table perspective because we like the visual perspective a lot better. I certainly do. And so we want to come up with a way of visualizing what a vector field looks like. And again, to do that, what we're doing is computing at a variety of different points in the xy plane the direction vector that vector field spits out at that point, and then we're placing that point with its tail, its initial point, right at the location that was specified. And so to do that, really technology is the best way to do this, especially if you want to get a lot of different vectors down at the same time that can give you the best sense of the overall behavior of the vector field. And so I've got a GeoGebra worksheet that's linked in here that you are not only welcome, but kind of, it's going to save a lot of time for you to use on this. And so to use it, you are going to have to change a formula in here to actually use the vector field that you're hoping to use. So the one that's loaded up here is not the one that's a part of this activity. This one is x minus 2y comma 2x plus y. And so if you want to use your own vector field, just replace this first line here in the GeoGebra with f of x comma y equals, and then in parentheses put the components of the vector field that you're using. So if we're doing y comma x, and so this would be the vector field f of x and y is y comma x. This blue point over here can be dragged around to wherever you need it to be. And so if you're looking for a specific locations, you can just drag that point around and read out what is the coordinates, the components of the vector field at that point. One thing to notice, by the way, is that in this vector field, some of these vectors are longer than others, right? So the vector field is encoding both magnitude and direction at each point because the output is a vector quantity. But another thing that's true is that if you look at this vector here, the output for my vector field 0, 3, it really should have a length of 3, right? This vector should extend all the way up here to 0, 3. The problem is that if we were to draw all of these vectors in exactly with the magnitude that they actually really have, the vector field looks kind of sloppy and scary. And so very often when technology is used, especially to visualize vector fields, it sort of scales the vectors down a little bit just to make the directionality easier to see. And so you can always believe the direction that you see on a technology-generated plot of a vector field. You can't necessarily believe the magnitude as an absolute magnitude, but you can believe the magnitudes on a relative basis. So where the vectors are longer, the vector field has a higher magnitude. Where the vectors are shorter, the vector field has a lower magnitude. So part C then, and part D also, is about just coming up with visualizations for the two vector fields that are a part of this preview activity. And in GeoGebra, once you have a picture that you like, use this hamburger menu in the upper right-hand corner, and export image is the best way to get a nice, high-quality graphic out of GeoGebra. It's going to come out in a PNG format, which is kind of one of the nicer image formats. It's a little bit larger file size, but it really gives a nice visualization to come out rather than using a screenshot. Export image is a little bit easier way to go. All right, so you had an opportunity to just use a GeoGebra worksheet to visualize the vector fields from this first activity. The vector field f of xy is y comma x, looks like this. By the way, those of you taking linear algebra with me this summer will recognize this vector field as actually something we could represent with a matrix. Right? F of x comma y equals y comma x. That's the same as f of xy as a vector is equal to the matrix 0, 1, 1, 0 multiplied by the vector xy. And it turns out that the properties of that matrix actually explain the properties of this vector field. If you notice how this vector field is kind of pinching everything in towards the origin along one diagonal, and it's pushing everything out away from the origin along the other diagonal, it turns out that there's a property of that matrix 0, 1, 1, 0 that tells us both of those facts at the same time. It's actually the eigenvalues and eigenvectors of that matrix. But anyway, for linear vector fields, there's a really nice way to understand them using the tools of linear algebra if you happen to have them at your disposal. The other vector field also ends up being linear, interestingly, right? It's g of xy equals minus xj. And here, all the vectors are either pointing north or south. All the vectors with a positive value of x, so in the right half plane, are pointing south because it's minus xj, right? And all the vectors in the left half plane, to the left of the y-axis, are pointing north. And the magnitudes are getting larger the further away that we get from the y-axis because that's where the value of x, the component of the j component, is getting larger as we get further away from the y-axis. So having one of these visuals is probably the best way to understand sort of not just globally what the vector field shape looks like, but also kind of locally what the vector field is doing at each individual point in the xy plane.